I think I got it. Probably what had happened was X was caps and I did it small. So shift run. Okay, good. So it is accepted now. So predict output. So we have got the Y predict run already. Now in this equation, YPRED is the predicted value column. Regression model is the regression model we generated by training the data, and XTest is the test data array. So below we define another table data frame DF that has actual test values listed in a column named actual and the respective predicted values in a separate column predicted. So let's do that part now. DF, let's define a new one. DF equal to PD dot data frame, D caps data frame, round bracket. Now we define a dictionary here. So open braces, open quotes, actual. This is the column name is to Y underscore test, comma, single quotes, predicted. This is another column. These will appear as column names, and under predicted column we will have all the Y underscore pred values, right? Now let's check first 25 rows df1 will define another. Now we know already this instruction df dot head 25. So what we are doing here, so we are just comparing actual values and predicted values. In a data frame we are going to create called df, and out of that 25 rows will be another copy called df1. So let's do that part. Shift enter. So we have created this part. Now evaluation of the performance. We have already run the model. We have generated the output values. We are going to evaluate the performance now. Essentially, under validation, we want to check how accurately the algorithm has predicted the mileage. For that is, compare predicted values with the actual values from the test data. We shall do three types of validations. First one is the visual check. Second one is the percentage predictions, where the predicted versus actual error is say within plus or minus 10% variance. See, normally this will be defined by some user, some client, that we want so much accuracy within this limit, and you should have so many percentage of samples at least, which will conform to this accuracy. So we are setting up a 10% variance, and we'll measure this again. This is the benchmark we'll set, and we'll compare against that. Then third one is the root mean square error percentage, which is the statistical benchmark. This is actually universally accepted one. So now we will do a visual comparison. Below bar chart represents a comparison between individual and predicted value and actual value to get an idea. This is a standard plot syntax. So let's copy this instead of typing it one by one. So I do copy, and the first part will simply paste here. Okay. So let's go run through that instruction. df1.plot. Okay. So this is matplotlib, which is going to plot it for us. Then kind equal to bar. We want it as a form of bars. Okay. Figure size 10,6. This is the size. You can change this option to whatever numbers you want. Now, which is major axis, which is minor axis. These are all finer points we want to set there. The different colors, what colors of bars we want, green, black, blah, blah, whatever. So this is all standard process. You would be knowing this. So I'm just not going to go into the details. And then plot plt.show. Shift enter. Okay. So here is the bar plot. This is actually giving us just a quick check, a visual representation as how the predicted and actual values, how close or how far these are. Okay, actual and predicted, we are just comparing. So this was the first type of check we did. Now these two are important. Percentage prediction within tolerance. Now this I found in the industry, this is most relevant. We shall record the entire test output generated and calculate how many predictions are within plus or minus say 10% variance, as we discussed. See, this will generate an Excel sheet which will be saved on my C drive. Similarly, you can give a path where you will want to save it on your drive. Okay, and then you can open and take a look at how the different columns are appearing. I'm going to give a snapshot below, which is the performance we are expecting to get out of this data. So initial performance. So let us do this part first. Prediction with tolerance. Okay. Now within tolerance, df0, it will define another data frame here. df0 equal to df. This was our above data frame, earlier one. df.head 79. Why 79? Because we have 79 test samples. df0 dot 2 underscore 2 CSV. This is a standard method. You must be knowing this. df0 dot 2 CSV, and then I'm going to give the entire path. So I will just copy this path. You can whatever path that suits you. Control C. I'm going to put this path here. C:/users was cars out base. So this is the base run. So you can name it as cars out base, and this will keep record. We'll compare as we improve the performance. Now shift enter. So this instruction is run. It has generated an output here. So instead, I won't spend time in looking at that. I have given a quick summary here to save the time. So this is the kind of look we are getting at the Excel sheet. Actual, predicted, error percentage, percentage prediction within 10%. So this is not a very great accuracy we are getting here, but we are going to improve this by a couple of changes that we will discuss it next. Okay. So this is now saying 57% of the predictions are right and 43% are off. They are outside 10% variance. Now, the third type of thing that we are going to do is, again, this is a standard syntax. So let's not spend a lot of time on typing this. So there are three things: mean absolute error, mean squared error, and root mean squared error. Our main interest is root mean squared error. So these steps are just to know step by step how things are there, and so that we can look back and check. It's not, so this is something that you can try it out by yourself and get a feel. Right now I'm going to get the numbers finally. Shift enter. So mean absolute error is matrix.mean absolute error. So this is matrix is one of the libraries. I will just, we must take a note of this. Matrix is the library we imported from Pandas Python standard libraries. Matrix.mean absolute error. So this is their own field, and we are going to compare y-test, y-pred. So likewise, we have matrix mean squared error and matrix.mean squared root mean squared error. np.sqrt will get the square root of this. Now we'll run this instruction. Shift enter. So we will not go into all the details. We just look at the final value, that is 2.978. That's almost like 3. So 3% is a root mean square error we are getting. This was our like baseline performance. We just did nothing special. We just ran the trained data set, split into train and test. We ran the model, we generated the output, and these are the results. Okay. So now we are going to do first level of improvement in the performance. Now let's see how we will do this. First, now, okay, one more thing. We have gone instruction by instruction. So the same instruction will be repeated again and again, couple of times. So we will not type each and every instruction one by one because we already seen it up there. So I'm going to copy a bunch of instructions and run it straight away. So we quickly generate an output. So improvise performance. First approach, select only 4-cylinder data. You remember that up there we created a library called 4sil. Let's check we have done that part or not. So let me try one thing. I do not remember if we ran that instruction or not. df underscore 4sil dot shape. Shift enter. Okay, so we have it here. So as we remember, we had split the data, that is 394 rows, into the maximum number of 4-cylinder car models. Okay, so these are about 50%, 201. So we have picked up a section of that data of 201 rows and 9 columns. So we will straight away plot a scatter matrix here that we have seen to save our time. This will kind of show us the behavior, but we kind of know how they are related. So I will just, remaining is going to be repetition of what we did. All we are doing, what special we are doing is, we are, instead of having a mix of 4 cylinders, 6 cylinders, 8 cylinders, we are segregating 4 cylinders together. They are machine learning. Normally the principle that we need to remember is, the more homogeneous data we have, the better results we get. So by keeping 4 cylinders separate, we are expecting to get a better result. So let's see how this happens. So I copy this here. So we generate a scatter matrix for DF4 SIL, shift enter. Okay, so it is generating the matrix for us. So we can take a look. Okay, if we scroll down here, now this is showing us the behavior. Now here this is showing, what we is showing is, we are having only half of the data here, but more uniform data. And we are seeing that the displacement, these are all displacement, these are bivariate plots. Mileage is plotted with displacement, then number of the year, the weight, the displacement, and all these fields. And we're going to repeat the earlier process once again. So set up the data. So I will just execute a bunch of instructions here. Set up the data, predictors, and target variable. So this is a repetition of what we discussed earlier. For DF4 SIL is our, then we are pd.getDummies. Again, we are going as before. Origin field, we are going to get the categorical into numeric values. Then we are defining X, we are defining Y, we are splitting train test, and we are setting up the data for the model. And finally, it will check the X test.shape, that will give the shape of this. Shift enter. So out of this, what comes out is, we have 41 rows only and 8 columns as the test data, and remaining out of 201, that's roughly 160 are train data. So define and train the model. So let's go to that step now. So again, we will execute a bunch of instructions here. We will not waste time in typing this once again, because you can try it out yourself and see how it improves the model performance. Control V. So shift enter. So here are the coefficients. We have generated the predictors and the coefficients. Next one is predict the output. So these are again repetition of what we did earlier. Control C. Now quickly come to the evaluation. So evaluate the performance of algorithm. So we have made one level of modification, that is, we have kept only 4 cylinders samples. Essentially, under validation, we want to check how accurately the algorithm has predicted the mileage and compare. Just a minute, let me get to the right place here. So we'll check the visual comparison. So this I'm going to run all at once. Copy from here and I'm going to paste it here. I would like you to try out all by yourself to get a feel. Okay, this we have done before, we are redoing it. Shift enter. This is for the improved performance. We see that, visually see that the values are coming pretty much a bit closer. Then we'll see the second type, and we'll analyze what was our findings. So predictions within tolerance. So let's check how we are doing on this front. So we copy these ones and run it here. So this is going to generate like above 4CL out, this output. Now below I have given a snapshot how that looks. So this has improved, not a lot, but somewhat, at least about 10% of more accurate readings, predictions. Now let's check on the root mean square performance. By regrouping data, what we find here, into a homogeneous group of 4 cylinders, we have improved the accuracy from 56 to 63% prediction and within 10% tolerance. Also, maximum deviation has dropped from earlier highest 65% to a new lower value of 27% of the mark. So the highest deviating point it has come closer. So we are improving somewhat, but we'll still do better. So we'll see how. So again, I'm going to do this RMSE thing, which we did earlier, and we'll see the values once again. In the end, we will take a stock how we fared. Shift, enter. So this actually it went a bit higher if you see, due to insufficient training data. Now this is an important point you want to learn, because this experiment and doing multiple trials, what we are trying to do is how we are improving it. But everything will not work exactly the same way. Due to insufficient training data, the RMSE error in this case is marginally higher by 0.4%. Not 0.4%, but 0.4. That is, it has now increased to 3.39 minus 2.98 earlier. So let us see how we can improve this. Now improve the performance second approach. In the above trial, we found that the data became more homogeneous. These conclusions are important to learn from this. In the above trial, we found that the data became more homogeneous when we applied filter to select only 4 cylinder data. However, the training data also reduced to half the size. Smaller data sets resulted in insufficient training during machine learning. This is called underfitting. You don't give sufficient number of samples to the model get trained, so that does not give a great performance. So since we cut down the samples from 79 to this 40 something, so almost half the size, 41. So it was almost half the size. So that has deteriorated the performance. So let's see how we can make this better. Secondly, there was considerable variance in the data. So data also had a lot of variance. If you see the scatter matrix that we generated, there we see there is a lot of scatter in the individual values. So that also causes a lot of variation. It is now we'll discuss all of this in the end. So this has resulted in higher RMSE. Therefore, to check whether the accuracy could improve using larger data set, I have added some dummy data. So there are some scientific methods of doing this. But right now I have added some dummy data just to get a feel, just to tell you how we can improve by giving more data. So let's execute these instructions. So this is one more data set. You can just add some dummy rows to that. What I have done is I have actually sorted the data and took more of later part of the data. Okay, so the period that was covered by the data was from 1972 to 1982. So what I have done is to add some more samples, I have copied some rows from 80 to 80, from year 80 to 82, and which then that time maximum are showing Japanese ones, and they are more uniform and they are kind of better with fuel efficiency. So we have more uniform data and we have more samples now. So that is in a nutshell what I did to create the data. You can create similar thing, or I can share this with you. So let's execute this instruction. I'm going to now load and prepare also in a quick shot. This is again we did earlier and we are repeating it. So I'm going to redo this. So just copy these instructions. We have done it earlier. Control V. So DF4 dumb is having some dummy sample. That's why I named it as like that. This is the data frame. pd.read excel from my path. This is the Excel sheet with the added rows. I have created comparable rows almost equal to our original sample, but all with 4 cylinders. Skip row 0. Again first row to drop the first row, and df4 dot shape. Shift, enter. So this I have created sample. Earlier was 394. This one is 396. Almost same, and 9 columns as before. So next instruction, df for dumb is null.sum. I'm going to save time now. Just copy the earlier instruction. We have done all of this earlier. So here we see in the horsepower there is some bad data. So we're going to visualize that. We have visualized this and we're going to remove this. Now to remove this, we are going to change this by fill na.mean and then create the sum once again. So this we have seen earlier. I'm only doing something we did earlier once again. So copy paste and run it again. Shift enter. So now I have corrected all of them to 0. So all data is good. Now set up the data. So like the above one, we'll also visualize this once. I'm going to create one more scatter matrix plot just for our visualization. So this is the standard process. You must not skip this just to get a feel. But you can, while you do this, you take a look. You try to learn how those things are, the various correlations between variables. This scatter matrix basically is for correlation. So here we are seeing some scatter, some more concentration of some data. So similar pattern like we have seen earlier. Here are the histograms. So where incidentally what you should remember is when the column and row are same, MPG versus MPG, there we have the histogram. So all this we are seeing here. So each histogram and each bivariate variables. Not all variables correlations are important. We need to stay focused on what is our predictor variable and what are the impacting variables we need to look at. So again we set up the model like before. These are the same bunch of instructions we're going to re-execute. Set up the data, define and train model. So here we have 80 rows. Earlier we had 79. Here we have 80. So it's almost comparable. So all are 4 cylinders and all are more uniform kind of. Let's see how this performs. Define and train model. So regression model we're going to define and coef_df we're going to generate. So I'll add one more row here below this to run this bunch of instructions. Control V, Shift Enter. So these are the coefficients. Now we are hoping for a better output. Let's see how it comes. Predict the output. Ypred equal to regression model.predict x test. So same process again, and pd.dataframe we're going to create another data frame, actual versus predicted, and we're going to compare the results. Control C. We're going to predict the output now. So now visual comparison. So let's see if this looks better, just to get a feel. Visual comparison. Let's do the visual comparison now. Pretty close. They are looking much better now. Now let's see how they are faring on the other fronts. As expected, by increasing the input samples, we have substantially improved the prediction within tolerance. Let's see that now. Now this is an important thing for us to observe and learn from. So this is now executed. Now what we see is the accuracy is very much improved now. Why it was improved? Because all the data is homogeneous and we have given more samples, right? So we have percentage 22.5% are off and 77.5, nearly 80% have come closer. Now if we have more, you can even extend this concept to more closer and more homogeneous data. We'll discuss this in the end. So how we can do better and better on this performance. So root mean square error, let's see how it is. So we are a bit better on this front also. Earlier the very first was 2.98, then we improved it, we made it worse by cutting down we are giving insufficient training machine learning samples. So that went to 3 point something by 0.4 higher. Now it has come to really in good values. We are getting 2.78. So again it has become 2.78. So now this is most important. Let's come to the conclusion and roadmap for future improvement. So is this all we can do as improvement? Not at all. Rather, this is only the beginning of the infinite opportunity of handling real life use cases. Note that by better grouping of data and then by adding sufficient number of samples, we reduce the highest error percentage from 65% max to 27% max to 17% max. Then This was the highest deviation from the between predicted and actual. So that we reduced considerably. Improved the number of accurate predictions by initial low 56% up to 63% and then finally 78%. So which is pretty good. Improve RMSE from 2.98 to 2.78. There is a lot more that can be explored. For example, increase the number of samples. We should remember machine learning performance improves by large number of samples. Try for uniformity of data. Like for example, we get larger number of US models. Could we get data covering a year or two? We have 10-year data. So maybe if we have narrower range, there's a better chance of predicting closer. Then can we have a single model? We had whole lot of models that we are putting in the data. So maybe we could try out for single model. Another area to explore is use of scaling to make the data same order of magnitude. So this needs some explanation. So if we just scroll up, let me take you up a bit. If you see, this predictor and coefficient. If we look at this table, we see that 0.02%, 0.06%, these are the importance that model learning is indicating as how much a variable is important. Now you see here that the year is giving 1.0006. Then these are the importances it has given. So actually what we should do is the numbers, basically as we discussed, the machine learning model only understand the numbers. So the order of magnitude matters here. See, in the case of weight, it is the numbers are 4-digit numbers like 2000, 3000 kgs, right? Then in the case of MPG, we have like in the tens, like 30, 40, they are the mileages. So year is 77, 78. These are the numbers. If we see in the machine learning, the standard process is normally if you bring all these to the same scale, then the machine learning model will learn better. So these are the things that can be explored in detail, but I'm just giving you pointers here, but these are the things that can improve. So scaling is one of the things that can go on. Then scaling, okay. Then consider additional parameters to classify data like distance traveled, time taken, age of vehicles. So we have taken only weight, whatever was available. So this list can weight and displacement and horsepower. These are the factors we considered, but there can be few more which are actually impacting. So this is how we solve the real life problem. The list can go on. On the final note, we could also extend the application for a car manufacturer or some third party application to conduct large number of tests and say in an area based or city based to advise more realistic estimates to the customer on the mileage on the basis of road conditions, traffic jams, signals. So all these factors also contribute in terms of time taken and mileage. So with this, we conclude our discussion here.